So this question, we are looking at a situation where we have a vector in a vector space V, and we're looking at this SV, which whenever we say SV equals something, we got to see what that is. And it's the set of linear transformations from V to W, where T of V equals 0. So I'm looking at linear transformation. So T1, T2, T3, etc. These are my vectors, and the property that they have is Ti of V equals 0. And it's not for all V in V, it's just for a specific vector V. So we want to prove that this is a subspace. So our two things for proving a subspace is first non-empty. And when we're looking at linear transformations, to prove non-empty, we prove it either has an element or we have the 0 element. And here, if I look at it, Z of V equals 0 as Z of V hat equals 0 for all V hat in V. So no matter what vector in V we have, the 0 linear transformation of V equals 0 in W. So this means thus Z is in SV. And remember, we're considering linear transformations. The vectors that we have in our set are linear transformations. Now we have closure. That's what we're proving next. So let S and T be in SV and F or C be in our field. Then C T plus S of V. And now what we're looking at is we're looking to see if TC plus S, that linear transformation, is in this set. So when I apply it to V, this should equal 0. Well, let's now use our properties. This equals CT of V plus S of V by definition of addition of linear transformations. Well, this equals C times 0 plus 0 as T and S are in SV, which equals 0. Thus, CT plus S is in SV. It's an element of this set. Therefore, SV is a subspace. We've proven it's non-empty, we've proven closure. The key here is we want to consider CT plus S. We're considering this new linear transformation. Our combination of vectors is that linear transformation. Okay. So now we have an isomorphism, and we want to prove that a set is linearly dependent if and only if this set is linearly dependent. So we have got our forward direction to prove, and we've got our backward direction to prove. So to prove the forward direction, suppose the set V1 through Vn is linearly dependent, then there exists a linear combination A1V1 plus A2V2 plus AN Vn equals 0, such that at least one AI does not equal 0. Applying T to both sides, gives t of a1 v1 plus all the way to an vn equals t of 0. Now, at this point, you might be saying, well, that means we've got our linear combination, but we need to show that this equals the 0 vector in W. So we need to justify that. So A1 V1 plus AN Bn equals 0 as T is a linear transformation, which implies that A1T V1 plus A2T V2 plus AN T Vn equals 0 with as T is a linear transformation. As at least one AI does not equal 0, the set T V1 through T Vn is linearly independent or linearly dependent. Sorry. So we've proven the forward direction. Now to prove the reverse direction, I'm actually going to do it here. It's going to be very similar. So the reverse direction, suppose the set T V1 up to T Vn is linearly dependent, then there exists an A1T V1 plus ANT Vn equaling 0, where at least one AI does not equal 0. Well, this implies that T A1 V1 plus AN Vn equals 0, which implies that the A1 V1 plus AN Vn is in the kernel of T. As T is injective, the kernel of T equals the set containing 0. Thus, A1 V1 plus up to AN Vn equals the 0 vector. As at least one AI does not equal 0, the set V1 up to Vn is linearly dependent. And we have proven the other direction. Here, B6, I am going to leave as an exercise. This is something that I have highlighted that you should practice. The one thing I'm going to say is that our left-hand side should start as T R plus S of V, and our right-hand side should be T R plus TS of V. That, or of U and of U, that's the hint I'm going to give. The rest of it you should do. Well, remember appropriate justification.